Ladies and gentlemen, so we talked about my feelings. We talked about public policy in various ways. Let's move closer into the games. A big part of games is obviously technology, the software. And I have a special guest for you. Hands up. You don't have to raise your hands. I know you've heard this word, artificial intelligence. But can you say anything what it means? Everybody talks about artificial intelligence. Here's one person who can explain what it means. I have for you Martin Singh Blom. He's a senior research engineer at Embark Studios, here to give the keynote speech on games and automation, creativity, and the future of game creation. Martin.
There. That's my slide. Yes. So, Per asked me to give a title quite a long time ago. So I didn't really know what I was going to talk about. So I gave something kind of vague and nebulous. Automation, creativity, and the future of game creation. But it could, maybe, I realized as I was working on it, have been named something like proceduralism, machine learning, and video games, which is a little bit closer to what I actually do, but more like technical words and stuff like that. And then as I was working more on it, I realized that the actual title maybe should be How to Animate One Robot in 3 years using just 6 engineers and far too many dollars in cloud compute costs. So this is what I'll be talking about, and welcome to my talk. Who am I and what do I do? I work at a company called Embark. It's a fairly new company in Stockholm. That's me in the background, leading us the door. We were formed by a bunch of people that came from electronic arts and DICE mostly. So this, like the very epitome of AAA, maybe one of the AAA-est studios in Sweden. And the founders had this idea that it's too hard to make video games, too hard to make AAA games at least, or too hard to make video games in general, actually. And we can make it easier with modern technology. So first start about too hard. Like, what's too hard about it? Well, so how is the video game sausage made? Let's first start looking at this short video from an upcoming game from Embark, and you'll get a better feeling for what I mean. Sound? Maybe I don't have any sound. Sorry. Yes, so lots of things moving, lots of stuff that you see. There's rocks and stuff like that. There's things. Lots and lots of things that you saw, right? And when you think about it, it's not obvious like what these things are. Like everything you see in a video game, it's a thing. Everything you see is an asset, we call it. And that's rocks, that's shrubberies, that's player characters, that's enemies. And they all have a lot of detail, right? Like in a AAA game. This is some kind of 3D model that you put into the game in some way. And this is not just true for things. Let's talk about motion, for instance. So here's a character in the game jumping. Someone has to make that. Right? Like, how do you make that? And this is true for sounds. For the dialogue, someone has to write it. That's easy. Like people have written movie dialogue and stuff like that. But in a game, you have to be able to interact with it. How do you do that? Visual effects, like explosions and stuff like that. That's also something someone makes, right? So let's move to the part where I talk about how we can make it easier with modern technology and how we make these things in general and how modern technology helps. So, what are our options for making things in video games? I'll go back to talking about. Oh, sorry, this is where I am. You can make it by hand, right? I'll show more what that means for some specific cases later. You can make it by hand. You can transfer it from reality in some way. Like in reality, we have lots of things that we can use. Can we get them into the computer in some way? And then we can use them in the game as well. Or we can create them using proceduralism. We can make computer programs that creates things in games. Right, so let's talk about things now, again, back to the things and rocks, right? So the traditional way, the making by hand way of making things in video games is by making models in some kind of 3D modeling software. These are trees. They're nice, they look cool, but they're not like AAA photorealistic trees, right? And And you can do that maybe if you do it, like if you have an artist spend like a month, they can make a rock like this. But that's a lot of work for one rock. And we have a lot of rocks, right? So there's a problem. It's too slow. We can't do all of this work by hand. Some parts here and there, yeah, sure, but not all of it. So one solution that we work a lot with at Embark is photogrammetry. And that's taking pictures of things. This is transferring things from reality into the computer. You take a lot of pictures of things. We send out the artist team to this is in Tenerife, I think, to take pictures of stuff that they think look cool. And then we pop these pictures into a computer program, and they stitch together some kind of 3D model. And then once you have a rough 3D model, you need to like fix a lot of problems and bugs with it, and something, the computer programs will have made mistakes and stuff like that. You correct all of those, and then after a while, you have a high quality model. Then you need a lower quality model in the game to be able to show lots of these things at the same time, and so on and so on and so on. So like, there's a lot of work still, but at least it's much faster. And now the third option I talked about, like the first one was make by hand, the second one was transfer from reality, and the third one is proceduralism. And what is that? What I mean by that exactly? Well, proceduralism is an old idea in video games, and this is like one of the real classics. This is Rogue that I'm showing in the background. It's a video game where you're an adventurer walking around in a system of caves, encountering lots of different monsters. And the cool thing about this cave, these rooms, is that they're all generated programmatically, right? So instead of having an artist say, here's one room, next to that one there's a small corridor, and then there's another room, all of these things get built by the program. So you like input some kind of random numbers or something like that, and then poof, you've got a cave. And so every time you replay the game, it's a new cave and a new system. So you create a function or procedure that takes some kind of random number to make things different every time you do it, and some other parameters that like decides how caves look, and you create a cave. And asset creation now is the art of creating procedures that give pleasant results. Yeah. And that is also a kind of tool we use a lot in Embark. So here's a table that one of our artists wanted to draw. And this is kind of in between drawing by hand proceduralism. So they draw out the frame of the table. They mark up, like green is metal, brown is wood, and then they have some guides for like cracks here, welds are yellow, stuff like that. And then they click a button, and poof, they get a table, like magic. So that's really cool. This took 15 minutes for Max Vasquez, 3D artist in Embark, from start to finish. And that like speeds up things and makes it possible to do things, to increase the amount of things we can have in the game. Right. Another example is by another colleague of mine, Anastasia Para, who made this demo for how to build little houses. And I like this picture because you see very clearly what the process is. First, the program starts randomly taking a block at the bottom with some kind of width and some kind of length. And then you put a random box on top of that with a slightly randomly angled roof angles. And then for each side of this thing, you randomly put out a window. And then for each wall that you have, you randomly put in planks of various thicknesses and stuff like that. And suddenly you've got a unique house just at the click of a single button. She just clicks a button and poof, there's a new house. So now if she wants a lot of houses, she can just click the button a lot of times and go like, oh, I didn't like this one, I didn't like this one. This one's cool, I put it here. Didn't like this one, didn't like this one. This one's nice, I'll keep that one. So that's really cool if you want to make a lot of houses. But you need to know the rules, right? So the artist now needs to know the rules for how to get aesthetically pleasant houses. And Anastasia, luckily, is a really good artist, so she does. But some things are just hard to figure out the rules for. Like there's too many parameters that you need to figure out, too many choices you need to make in how to make these, set up these rules. So then you might ask, why can't we just make the computer figure out the rules for us in some way? That's a great idea. That's what we call machine learning. Yeah, or artificial intelligence or something like that. So what is machine learning? I'll actually now tell you exactly what it is. It's known it's a very popular word these days. Like it's also known as artificial intelligence, neural networks, differentiable programming, deep learning. And artificial intelligence, especially in games, is a very fluffy word. Right? Like it's very not precise what it means, because you both have the AI for the enemies in the game that goes around and does stuff, and then we have this machine learning AI kind of programming paradigm that you talk about. But in this talk, I'll talk about it in the sense of a new programming paradigm, a new kind of programming where you program by giving the computer examples. So that's all there is to it. So in a traditional programming, in a traditional procedural programming setting, the artist will figure out the answer to all of these questions when they make the house generator. Like how wide should the base of a house be? How long? How many windows should we have? Do houses have awnings? I don't know. How common are stairs? Like all of these things are choices that the artist has to make, and set some kind of like 90% of houses have one stair, but 10% have 2 stairs or more, and like all of these things are choices the artist has to make. But if we have a lot of examples of actual houses, we can just have the computer figure this out. And in machine learning, that's what we do. The computer figures out the details of the procedure based on examples given by the programmer. And in deep learning, which is the most popular form of artificial intelligence that has made the whole field explode in the last 10 years, the procedure is always of the same kind. It's deep artificial neural network. Those are words. What does that mean? Yeah, it's actually fairly easy. I'm going to show you exactly what a neural network is. So this is an artificial neural network that I've drawn here, a diagram of. And it has one number that you put into it and one number that comes out of it. And inside of the neural network, there's a bunch of rules that determines what input number corresponds to what output number. Okay. And the input number is the green circle, and the output number is the yellow circle. And all of the lines are the rules. And almost all neural networks that you see today, when people talk about Siri, self-driving cars, I don't know what, fake news, all of that stuff, it's all using exactly this kind of program. And each arrow here is a number. You multiply the input number by that number, and that goes to the next line. So if you start off with 2, we multiply that by 5, that gives 10. We multiply that by -2, that gives 0, because if it's below 0, you just set 0. And that's the magic of the whole neural network. and then when you go to someplace where you have multiple arrows pointing in the same way, you just add up all the numbers. And if whatever you get at the end of that is below 0, you just let it be 0, otherwise you take the number that you get. That's what we call a neural network. Why is it called a neural network? Well, it's because it's sort of kind of, if you squint a little bit, works like a neuron works. So neurons have lots of different connections coming into them, and the neurons fire, and when they fire, they send a signal through these connections. And the next neuron in line that gets the connections coming in only fires in its turn if the firing is strong enough. So if it goes over the threshold. If it's below, then it doesn't fire, so then we get 0. If it goes above the threshold, then it fires and sends out signals to the rest of the neurons in the brain. So that's why we call these artificial neural networks, because it's kind of inspired by how real neurons work. So now this is our neural network, and this seems like it wouldn't give you super much, but neural networks can be bigger. So this one takes one input number and gives 2 output numbers. Here we have one that takes 2 input numbers and gives 1 output number, right? And this one is a deep neural network. Why is it deep? Well, because it has a depth of 2 layers in the middle, 2 gray layers. That's the depth. And once we start talking about real industry-used neural networks, we have dozens of layers, and we have thousands of gray boxes, or gray circles for each of these layers, which means 1 million different arrows between each layer. So there's a lot of numbers all of a sudden. And when you have a lot of numbers working together, you can get really interesting things. Show me examples, you say. These are just balls on slides. So what are examples of this? These are all examples that we actually either have looked at Embark or actually use at Embark. Most of them, and I won't tell you which ones, but they're all kind of cool. The first one, the canonical example, is what we call image classifiers. This is stuff like Google uses this for figuring out when you do image search and stuff like that. So here we have one single neural network, and it decides if the picture is a dog or a cat. Dogs and cats, I said it takes numbers in. And actually, anytime when you see a picture in a computer, that's just a bunch of numbers, right? So a picture, it's maybe 200 wide and 200 deep. That's 200 times 200, that's 40,000 numbers. And then you have one number for each color, R, G, and B, red, green, and blue. So that's 40,000 times 3, that's 120,000 numbers for the cat and the dog, right? So you put in the 120,000 numbers, you go through a bunch of these layers and multiplications that neural networks do, and then it outputs 2 numbers. And the more it thinks it's a dog, the more it should be to the right-hand side, to the second number, the higher that should be. And the more it thinks it should be a cat, the higher the first number should be. That's what we call a classifier. And these are used everywhere in the industry these days. And it's super cool because 15 years ago, people didn't know how to deal with images. Like we had no idea. When I was in college, I took a computer vision course, and it was crap compared to what we do today. And that's just because of these new neural networks that have come out and makes it possible to do this very easily. Another thing is generating images. So then instead of pushing in these 120,000 numbers into the network, you take the 120,000 numbers and get them out of the network. So this looks like this when you start it off. So this is a neural network that hasn't been shown examples, that doesn't know what it's supposed to make out of these numbers. And then it just outputs noise, right? So it's like, I don't know what you want from me. Here's a bunch of noise. But then we find something that we want the network to generate, say faces, right? And we show it these faces, and we update all of the values for all of the arrows until it gets closer and closer to showing faces. And after doing that a few 100 million times, this is the stuff that comes out. And that's pretty cool. And they're they make mistakes, right? The glasses look funky. I don't know what the hand is in the second one up top. Like, it just looks weird. But the new ones are better. Like, this is from 3 years ago. And if you want to make assets in a computer game and you want to make faces, you can see how this would be useful, right? It can also, if you have the faces data set we just got by going to Twitter and Flickr, and typing faces, and then downloaded all the faces we could get, right? But if you actually go out and make your own data set, you can do even cooler things. So, this is what I wanted to say as well. Now that we have the procedure, now that we have the program to make the faces, we can also allow artists or people to tweak the rules for it, right? So, say that you've generated a face that looks like the blonde kid in the top middle row, right? And like, oh, that's a cute kid, but I would prefer him to be a redhead. So then you can tell the network, okay, now take the style from the redheaded woman on the third row there, and then we get the redheaded kid in the middle. So now we have like these rules for how we can modify it and stuff like that, because we've moved it from being just pictures in reality. Like we now have a computational rule that we can modify and play with in order to generate cool results. And I think it's obvious that this could be useful for artists and stuff like that. Say now that you have actually gone out and scanned people's faces. That's something we do in computer games in order to get, if you have a Marvel game, you want to have Iron Man's face in the game, and then you have to go out and scan it, and you put lots of dots on the face and stuff like that. If you do that for a few thousand faces, you can now maybe make an automatic scanning thing that just figures out what the scan should be just by looking at the picture. And that also saves a lot of work, because then you don't have to put dots on the faces of people and stuff like that in order to capture them into the computer. And we can use it for, this is me and my colleague Jack, for capturing movement as well, right? This is another thing that you've seen in a lot of, every movie does this when they have computer effects and stuff like that. They want to see where the body is so they can get it into 3D. Now you can do that with just a cell phone camera. And that's also just getting the picture in and outputting a bunch of numbers for where my left hand is, where my right hand is, and so on. We can create shapes in general with it, and that's super useful in games. I've talked about how we want to have things in the game, right? Now, say that we want to have chairs, we can take a bunch of pictures of all the chairs that we have available, and then have the computer figure out what the procedure should be for generating chairs, or offices, or fighter planes or whatever it is. You can generate music just by feeding it all the music we have available, and suddenly like you have something that plays kind of crappy piano. It's not great yet. It's getting better, but you can do that at least. And again, since you have it in the computer, you can also get some kind of measure of control of it and tailor it to the suspense of the scene or something like that automatically in the game. We can generate text with these same models. This one is from a fairly recent text generation model. This is what has led to the whole fake news scare around AI. This particular model, I think. And I think this one is hilarious, how to give your ball python a bath. But you can use this for you know, I don't know, fake Putin speeches if you want to, or cool dialogue in the game if you want to do that. Like it's a super powerful technology. And it allows you to be interactive with it. Like you can have a dialogue with these models and go back and forth. So now I'm giving you a bit of a background and like showing you a few examples of how AI are used in games. Well, am I on time? Good, yeah. So now let's get to the meat of what I've been doing for the last few years. I've animated one robot using a team of 6 engineers and lots of cloud compute costs. So let's talk about animations to give you a bit of background of what I did. So in computer games, a lot of the animations you see are actually hand-drawn. Like there's 2 big ways. Again, back to the how do you mostly make things in games. There's a lot of hand-drawn animations. This is Steamboat Willie by Walt Disney, and the principles for how you animate things don't differ that much in a lot of modern video games. You say frame after frame, state after state, like now the foot should be slightly higher, slightly higher, slightly higher. The way the animators actually do it is usually just they since it's all in 3D space in video games, they have some kind of curve in space for how the hand should move, and a lot of what they do in practice is like they design these curves. So like this one will give an excited movement because it overshoots slightly and then wiggles a little bit, whereas the maybe uniform 1-4-1-2 there in the middle is a bit more of slow movement, right? So like they tweak all these curves and get different behaviors out of it. But it's kind of labor intensive and time consuming. The other way that I'm sure you've seen is motion capture. That's the capturing things from reality and moving it into the computer way of doing things. This is the animation team at Embark, and our sound director, Bense, who also is a taekwondo black belt or whatever, the super champion, really good. So he's got amazing body control, and we use him as stuntman for our motion capture work as well. But his day job is to be a sound engineer or sound director. And here they go around and they have these suits that capture the movement and can like immediately move his body position into the computer and we use his movements as movement in the game. So those are the 2 main ways we've used traditionally. And then once you have all of these little pieces of movement, right? You connect them in some way because you have to like do that in the video game. So you have the character turning left and right and running forward, and you need to be able to have transitions between these different states. You need to like say, okay, how does it move its hands when it starts shooting? How does it go from standing still to rolling? All of these things. So there's a lot of wiring that you have to do to get this to work. And just simple things like this. Like you see, like this is the snippet I showed before, but with some debug output. Like you need to like decide how high should it be above the thing he jumps over. How should the movement be affected by the incoming angle, the outcoming angle, all these things. There's a lot of work to it. So when we joined Embark, the year before, there had been a few really cool papers about physics-based animation. So what is physics-based animation? Physics-based animation is taking the animation that you have in game that's normally just like these curves or like these cartoons with like movements that you have drawn or have captured from someone who's done them or something like that, and physicalizing them. So make them follow the rules of physics in the game, because games have physics engines that make sure that like if you drop the ball, it falls, and knows how to update step through time and make the things that happen in the game follow the rules of physics. And when you physicalize a movement, suddenly it's part of the game world, right? So suddenly now, if you so the reference character is just a motion capture character doing a flip. The blue one is a robot that we simulate in the game that does the flip. But since it is a robot, if you now hit the robot, it will fall backwards instead. And no one will have to animate that, because that would just be following the rules of physics in the game. Right? Does that make sense? Right. So we thought that was really cool and could lead to some really interesting gameplay. So we started off by trying to replicate the results. So here you see a ghost making a spin kick, and that's the reference animation. And this is our robot that makes the same spin kick and follows the same movement. So we could see that the technology worked. And at the same time, the game team and the design team and the art team were talking about what the next game should be that we should look at, and what we should be actually doing and making money from at Embark. And they wanted to have a game with big robots in it. And they wanted the robots to be physical and you should have these visceral, real interactions with them and bounce off them and stuff like that. And we thought that was a pretty good fit for what we were looking at with the physical animation stuff. So we started looking at small robots as well then, to see if we could make them move with simpler goals. So the previous goal for the previous physical thing that you saw was to follow the example movement of the example character. This one is just supposed to get to the yellow box as quickly as possible. And it seemed very promising. So I said, cool. Let's see if that works. So if this works, we felt like we kind of have a magic machine learning box that will give us robot movement for whatever robot we toss into it, right? So you take some kind of walker or War of the Worlds things or quadruped or whatever, you toss it into this machine learning magic box, and out comes an animated thing without animators having to actually spend effort and time on it. And we started prototyping this and seeing if we could get bigger robots to actually interact with the players. So in this case, the player is driven like a normal video game character is and not physically animated. But the big gray robot is all this physics-based actual simulated robot in the game. And the things we get for free are pretty cool. So I'd like you to pay attention when it turns here. You see the butt going down slightly? Like it goes like this a little bit? That's a pretty natural and smooth-looking movement that we just got for free by telling it to follow along and try to do your best. And stuff like that was really encouraging. So we said, yeah, sure, we can do this, nothing to fear. Whew. Yes, it was harder than we thought. So it turns out that animators are used to a lot of things in video games. They're used to having control and being able to say, okay, now the monster is about to attack. It takes this cool pose, right? And it was hard to get that to work because it's easy to say follow this box or follow this character, go to this thing. But it's much harder to in a well-defined way say, strike this exact pose or do this exact thing. So that was really, really hard. On the other hand, so the things that are easy to animators are really, really hard for us. But these kind of things are super hard for animators. Here it reacts correctly to every little box that gets thrown at it. It's not an impressive reaction in this case, but you see the neck goes a little bit every time it gets hit by a box. And that's for free. So the things that were easy are now really hard. And the things that were hard are now super easy. So it was an interesting place to be in. So now suddenly we had to turn animation from an art into science. And you may be good, science is good. But I have a PhD. So I can tell you science is hard. It's painful. You do mistakes all the time, right? And suddenly, instead of just telling the artist, okay, draw this thing, it should look like this, it should be cool, we have to keep lab notebooks, right? We have to say, okay, we've run this experiment once now, but I don't trust the results until I have them in triplicate, right? These are all different experiments we've run with okay, slightly increase the joint strength, slightly decrease the joint strength. Can we make it improve how much it prioritizes going forward and deprioritize how much it should be stable? All of these things suddenly become real engineering problems for us, right? We have to look at lots and lots of graphs to see is it progressing correctly, is it not progressing correctly, all of these things. So instead of needing animators that know art, which we had in the games industry before, we now need 3D artists that know robotics engineering, which is much rarer. But yeah, so the initial thing that Embark wanted to do said, well, it's too hard to make video games. We can make it easier with modern technology. Did we make it easier? Not clear. But we can have a look at what we got out of it, at least. Yes, so this is different. We can now animate a range of situations that wasn't possible before. So in some sense, we've made many, many more animations than an animator could ever possibly hope to make with this. And the range leads to emergent gameplay that was impossible to do with traditional techniques. Animators and game designers have to rethink how much control they have. Because now you just have a robot that follows the laws of physics. And we can no longer support robots that wouldn't actually work, which is a huge problem for 3D artists that just want to draw something cool and don't think too much about if it makes sense. And animation still requires skill, but the skills that we need for this are new and different skills than what we had before. So was it worth it? I hope so. But we'll see when the game comes out. And yeah, that's my talk. Thank you.
Wow, thanks so much, Martin. Please, we have a minute for questions, so think about any questions. That's also true for the people following us on the Zoom, because I am watching the chat and you can ask questions. I have already received one invitation for Innebandy Disco, so that's great. Martin, that's amazing. So, yeah, I think you have made us confused on a more interesting level.
Me too. So that's you're brought up to where I am. Yeah.
I don't think we're quite there, but thank you. It's funny how, I mean, the wasabi. I feel for wasabi when boxes fly at him. He's just a software simulation, and I still sort of give him emotion. I project emotion on him.
I think that's kind of what we think is one of the benefits of it, right? It feels so much like when you see computer game simulations frequently, I think that they feel unreal and like they're not actually part of the world, which has been a problem because the visual quality has become so high now. And then you get these weird-looking animations in the game. And this, to me, has made it hard to see animations maybe on other games and feel like they make sense. But these ones really do, and you feel like this is a real thing that's being put through these trials. Actually, like you can see it happening to it, right?
Mm. Yeah, it also says something about the human psychology, I think, but that's maybe part of the magic of games. And also, I thought about when you showed me all these AI-generated faces. Do you see a future where those faces would like have different mimics and start moving and talking? And,
that's done. That's happening.
Yeah. So you can generate a synthetic person.
Yes.
That can come across as a real person.
Yes, and with synthetic voice and clone people's voice or whatever you want to do. Yeah, which is useful for us in video games when you want to, for instance, dubbing is a thing that these kind of techniques could be useful for. Instead of having to manually get the faces to work with the new dubbing, you can just get the AI to move the face correctly and get that for free.
I mean, there's this mythos around not only artificial intelligence and robots. I think I mean, going back to Frankenstein or the golem, that man's creation will escape and bring down the downfall of man or something like that. Do you think, or do you fear that the synthetic persons will escape?
No, I don't, but I know that there are people that honestly do in the AI community. So I think it's an interesting debate to be had. It's very hard to get things to work, and I think it will be even harder to get things to work so well that they spontaneously escape. Yeah,
that's a comfort. Yeah. All right, I think we have a question from the floor, and I think we have no mic, so if I can ask Alonso to bring us a hand mic, that would be great. And in the meantime, I mean, maybe on a less mocking note around the escape, do you think, I mean, we talked about jobs before, do you think that procedural generation and the stuff that you showed us will take away job opportunities for real people?
No, I think none of these. Very rarely these kinds of new technology takes away jobs. Mostly it is a matter of enabling more content. So I think there are parts of the gaming creation craft that changes. But that's always been the case, right? Like you always have to, it's a living industry, you have to relearn new techniques every few years. But more people will be involved in the industry, and much better games will be made.
All right, cool. So I have a hand mic. I have one hand in the air, and it's none other than Dr. Malte Beermann, another old friend. Malte, good to see you. What's your question?
Good to see you. Thank you for this very interesting speech. I think that it's interesting that you also have artificial intelligence not only in the creation but also on the player side, and that you have games emerging which are supported by artificial intelligence to make it easier to play them. So a little bit, but it's a charming, nice event, so I can make some kind of joke. My dream would be actually a game which would be created automatically and distributed automatically and then played automatically. So that would be more like a piece of art, of course, not necessarily a commercial project, but that would be actually a really cool moonshot utopia, that you actually have a game which is created and played automatically.
I love it. Thanks, Malte. Yeah, let's. That challenges the definition of a game. Will you make this game?
I think I'll have to ask some government for funding first.
But it's an interesting. Let's say it's an interesting idea. It's a challenging idea. Okay. Thanks, Malte. Anyone else? All right. So let's say thank you to Martin. Thanks for sharing and educating us. And a big hand for Martin Singh Blom.